Okay. Hello, everyone. Thank you so much for joining. Thanks, Sanch and Erica, for inviting me and having me here. I'm looking forward to interacting with this group a lot. Give me a second just to manage my screens a little bit. Great. I'm also realizing I haven't given a talk on Zoom in a very long time, so forgive me if you notice some oddities in where I'm looking versus anything. Just uh, kind of weird to say that I haven't given a Zoom talk in a long time, but here we are. Hope you're all doing all right. Yeah, Sanj said I'm DK. I'm a um, sorry, moving some stuff around. Great. Yeah, so I'm an assistant professor at Colorado College. It's a liberal arts school in Colorado Springs. I Before that, I was a NSF postdoctoral fellow at Johns Hopkins University, and also worked closely with at Space Telescope Science Institute with Andy Fox's Milky Way Halo group. So a lot of what I'm going to talk about now is stuff I've been working on kind of since my PhD, with Andy's group, without Andy's group, just a lot of stuff. I don't know what I'm talking about anyway. But really what I want to talk about is using our galaxy, and especially the center of our galaxy, as an extragalactic tool, focusing on gas and the radiation field and photoionization happening in the Milky Way and how we can use that to better understand galaxies and galaxy evolution as a whole. Um, Also, just a little fun aside, if you need to find me quickly, you can go to my webpage, www.astronomy.dk. Great. Okay. So I'm going to start with a little journey through the to our galactic center from our kind of local viewpoint. So this is just an optical image from an amateur astronomer looking towards the inner Milky Way. I'm going to zoom in towards the center more. What these contours are showing is not from an optical view, but a K-band view of stars towards that same region that actually looks through the dust, so you don't see all those dark patches. In these contours, technically, if you kind of look carefully, there is a bit of an asymmetry where the left side might appear a little thicker than on the left side. The left side appears thicker than on the right side, and that shows up because of the bar, which is kind of angled closer to us towards the left than towards the right. And so that part appears thicker on the sky in projection towards us, which is just like a fun, very simple signature of the bar towards the center of our galaxy. Just look at where the stellar density is by looking through the dust at a different wavelength. I'm going to be focusing on optical light, though, which is a little bit weird to do towards galactic center. But even in this image, you might notice that there is some areas that are very dusty, that are dark, but also some areas that are very bright, where there's not that much dust. This one particular region here that I'm highlighting is called Bada's window, just a little bit below galactic center. And it gives us a way to look through towards galactic center, a little bit below the midplane, but close to galactic center, in optical light because there's not that much dust blocking our view there. So this is what we did. We looked at H alpha emission from the Wisconsin H alpha mapper towards this direction and found gas at these weird velocities that aren't consistent with anything except for something kind of associated with the bar. And it's tilted, which is what allows it to kind of stick out below the rest of the gas that would be associated with the bar and that galactic center region. So these contours are showing H alpha emission contours. What we did is look at not just H alpha, but also other emission lines like nitrogen 2, where we see changes in the nitrogen 2 to H alpha ratio, where local emission near the solar neighborhood has like one relationship, but towards this region near the bar, towards galactic center, that ratio of nitrogen 2 to H alpha is much higher. Nitrogen 2 is brighter than H alpha, which is a little unusual. But this is very common in other galaxies and something that when you look at other galaxies, you see and often associate these line ratios, these very high nitrogen 2 to H alpha line ratios, to a class of galaxies called liners. So what we found is that the inner Milky Way is one of these liner-like systems, and we can kind of now use our inner Milky Way as a laboratory to study what these liners are. And I'll describe what liners are more generally soon and kind of go into more details there. But my big kind of takeaway is that we can use our galaxy as a tool to understand these mysterious liner-like systems that are very common in other galaxies. So the kind of outline I'll go through is what I've just done is kind of talk about this discovery of looking at our Milky Way as our nearest liner galaxy. But I'm going to talk overall about diffuse ionized gas, both in our galaxy and others, starting with a little bit about like what are these liners, what's that connection, a little bit of a history there, and some possible sources of ionization for what is actually ionizing that gas, creating those weird emission line ratios. And then I'll go into the inner Milky Way specifically, brief history on the structure that we see in the inner Milky Way and models that we have with gas dynamics to understand what's happening there. And then I'll just kind of like flash through a bunch of different fun results of ionized gas near the center of the galaxy, mostly focusing on WAM, the Wisconsin H alpha mapper. So looking at this BPT diagram that's really common in other galaxies, but in our own Milky Way constructed with WAM. A modified model to understanding what that gas behaves like and how it all relates to the Fermi bubbles, the like large biconical outflow that is happening near the center of our galaxy. Okay, so diffuse ionized gas in galaxies in general. A really simple way to think about this is just to start with H2 regions, where you just have a hot main sequence O star. That O star emits Lyman continuum ionizing radiation that will ionize stuff around it, create a little bubble of ionized gas that we call an H2 region. So that's like the most simple kind of picture of an H2 region. In reality, if you look at what H2 regions look like, they're not perfectly spherical. They're quite fragmented and fuzzy and fractal-like. And that's because the density around them of the gas isn't uniform and smooth. So there's gaps, there's openings, there's inconsistencies. So that creates weird shapes. And it also means some of this ionizing radiation can escape and go much farther away from this kind of classically bounded H2 region. And that escaping radiation will ionize what we like to call the warm ionized medium or warm ionized gas. We mostly try and look at this. I mostly try and look at this at least using optical emission. H alpha, the like 3-to-2 transition of a hydrogen atom, watching it kind of cascade back in its recombination sequence. And the gas associated with this warm ionized gas is distinct from within an H2 region. It's hotter, it's much lower density, but we still think primarily, most likely at least, that is primarily photoionized by O stars. There's a lot of active research on what is causing the ionization, whether it's more diffuse populations of smaller but still hot stars are an active area of study. And I'll show some work on that later, maybe. I don't remember if I do actually. But some of the other characteristics we like can use to distinguish this gas from H2 regions, the observational signatures are especially come from those line ratios. So different optical emission line tracers like nitrogen 2, sulfur 2, oxygen 2 have unique ratios in H2 regions compared to this diffuse gas. So we have enhanced line ratios of those singly ionized metals compared to H2 regions, but lower line ratios of O3 to H alpha, which is very bright in H2 regions, but very dim in the warm ionized gas. We also see this kind of gas in lots of other galaxies, especially with lots of IFU observations happening now. Very common to see them in other galaxies. And the same emission lines are, your classical strong emission lines. So they're easy to observe in other galaxies. So they have been observed in other galaxies a lot and are used often in what is called this BPT diagram, which is looking at oxygen 3 to H beta on the y-axis and nitrogen 2 to H alpha on the x-axis. And a combination of observational constraints and models allow you to place galaxies or regions of galaxies on this space to identify what a dominant source of ionization for that gas that you're looking at is, whether it's coming from your classical main sequence O stars and active star formation in the bottom left area, AGN up at the top, so nuclear feedback, and this other like region that I'm pointing out to the right are these liner regions, which is just an acronym. It stands for low ionization nuclear emission regions. The N is in parentheses because often it's seen in like not the nucleus or the center of the galaxy, but in extended areas. That's been a little bit more recent, but it's just an acronym that describes what is seen as opposed to actually what is doing the ionization. So the source of ionization isn't really known for what that is describing very well. So these liners, these low ionization nuclear emission regions, what are they? What's causing the ionization there? This is just another BPT diagram now showing kind of a population of barred versus not barred galaxies, where in barred galaxies, the presence of these liners, these enhanced line ratios that are unique, are more prevalent in barred galaxies. There's a study using manga data that I did during my PhD thesis time. But in general, like for liners, some possible ideas for what could be doing the ionization. All of these like work, but it's not unclear which one is dominant, which one is more common, anything like that. But it could be low luminosity AGN. Strong shocks are able to create the same kind of enhanced line ratios. Or there's a population of hot, low mass evolved stars. So instead of main sequence O stars, like white dwarfs, subdwarf B stars, something that's gone through a different evolutionary path, or just later on in its cycle. That's still very hot, but very low luminosity, much smaller mass. So if you have a lot of them, it could add up, but you need a lot of them to provide enough radiation to account for, the gas that we see. This is also seen a lot in elliptical galaxies. It's associated with something that people have called the UV upturn frequently. And within disk galaxies, what this figure to the right is showing is that it's much more common in barred galaxies than those without a bar. So there seems to be some tie to a bar, and it's often seen far from the nucleus, which is why I have that N in parentheses. So let's go back to our galaxy, the inner Milky Way. I like to start with this picture, which is from a review paper, I think. Or, there's a narrative, the review paper in 1977 that Oort wrote. This figure to the right is from a paper that Oort is on from 1960 that is like a hand-drawn picture of what we think our galaxy looks like, especially focusing on the center of our galaxy. And it was always really interesting to me see this because there's the descriptions used. There was something out of the ordinary appears to be required, was what was stated in that review article. There's hints for needing a supermassive black hole at the center of our galaxy, which wasn't necessarily known at the time. And all of this was kind of linked to this idea that there's this expulsive phenomena, some like large outward flow of gas from the center, where we see lots of really high radial velocities towards us in the line of sight, which makes it seem like something is expanding away from the center of our galaxy. And the way this was classically kind of like put together, this picture was put together, was like identify little features in the observable space and associate them with like individual things like arms, complexes of clouds, rings, streams, all these like individual features that were individually kind of categorized and looked at that had these peculiar, really high radial velocities that made it seem like everything was kind of moving away from galactic center, from some explosion or something. Here's just a digitized version of that graphic that you might see a little bit better. But like literally, there's just like lots of question marks and speculation, which I find very fascinating how unsure everything was then, and honestly still is now about what the center of our galaxy looks like. Looking at this, we now know that our galaxy rotates. This is just an artist impression of our Milky Way. We don't really know what it really looks like, but an artist impression. Overlaid now is the velocity field for circular rotation that fits well with the rotation curve of our galaxy. What I want to really like focus on is that when you're looking towards the inner galaxy, the left side is going to be all red-shifted velocities, and the right side is going to be all blue-shifted velocities, all within the kind of like inner region. And that's just from galactic rotation and Doppler effect. So what I'm going to do here is construct a map of looking at just the exact opposite of that. Velocities that you shouldn't see in the inner galaxy because galactic rotation, just circular rotation, wouldn't allow for it. So just on the right side, only positive velocity gas, and on the left side, only negative velocity gas. So we should see a blank image, but in fact, we see a lot of emission and a lot of emission that connects smoothly across the center of across a galactic longitude of 0. through that kind of like discontinuous mapping that we are doing in velocity space. So this is what we call, this came together from a single unifying model in the 1980s by List and Burton, where they called it this tilted disk, where there's a gas layer that's tilted, it's elliptical, it's roughly aligned with the bar as we know it today, but it's tilted. It's not, it's warped. It sticks out below the rest of the midplane of the galaxy at large. And it's kind of like a warped part of our midplane as you approach the center of our galaxy in H1 gas, in neutral gas. And this is kind of associated with elliptical streamlines of gas that's moving along the bar's potential. The caveats from this like original 1980 model is that it's just a geometrical kind of approximation, ellipses that are tilted by certain orientations with a velocity field associated with it. It doesn't have any kind of realistic density structure, just a constant density that's tilted, lets you make accurate predictions for the velocity field of the H1 gas and like reproduce roughly what this distribution looks like. So if you want to get a realistic picture, we need to really look at hydrodynamic simulations and understand what that gas is doing. These are some simulations from Mattia Sermani. There have been newer ones that Robin Tress and Mattia have done that include magnetic fields and more feedback, but these are some original ones. This is showing H1 moving in a static bar potential. On the top is a face-on view, and the bottom is a view from the side. Here we like see a lot of that kind of streamlining motion, a lot of gas that gets funneled into the center of the galaxy along what we call these dust lanes, these dark kind of like pathways that the gas moves at high velocities. The caveats of this model is that while yes, it shows a more realistic density distribution, that density is really kind of confined to a relatively thin layer. The amount of feedback doesn't seem to be enough in a lot of ways to puff up the gas in the way that we see it. It's also very neutral gas heavy. There's no ionizing radiation field within the simulation, so there's a big lack of ionized gas. And really importantly, there's no tilt. All of this is kind of very flat and aligned with the rest of the galactic plane. It turns out it's really hard to tilt gas in simulations, and it's still a big question, why is the center of the gas in the center of our galaxy tilted in so many ways? There's this gas associated with this along the bar that's tilted at one angle. The central molecular zone within the more nuclear region is also tilted at a different angle. And it's not clear like where these tilts came from or why they are able to exist over long timescales. So we kind of have to use a combination of the information we get from more realistic hydrodynamic simulations, plus our kind of oversimplified geometric model to place gas in different parts of the galaxy. And what I'm going to focus on is looking at ionized gas that we looked at with WHAM. So if you're not familiar with WHAM, the Wisconsin H-alpha mapper, it's the most sensitive telescope of its kind in the world, really, really faint H-alpha emission from the sky. And it does that by looking at a 1 degree beam of the sky and turning it into a single spectrum. So terrible spatial resolution, but really great spectral resolution, very, very high sensitivity that lets us see the faintest of gas within our galaxy, and also the LMC and SMC. It's a National Science Foundation funded project. It's been going for quite a long time. It's still active and observing in Chile. And it's like a unique telescope that was first at Kitt Peak in Arizona and then literally shipped to Chile after it did a northern sky survey to complete a full all sky survey in H-alpha. We also have many other optical emission lines like H-beta, nitrogen-2, sulfur-2, oxygen-3, and all of that data, all the H-alpha is public. Many of the other stuff is like starting to be, and I have it and I'm happy to share. And you can use this Python package I put together to play around with it called WAMPy. So this is the tilted disk model that I was talking about, and it's kind of simple geometric approximation, but our modified version that includes ionized gas. So it's roughly aligned with the bar. It's tilted, and the ionized gas shows signatures that it's also flaring, but it sticks out just enough below that dust layer for us to be able to see part of it through that low extinction window. So here it is kind of roughly aligned with the modern day bar, even without necessarily knowing what the bar was like at the time. This just really comes from that original 1980 model of H1 gas. So we looked at this with WAM, found H alpha emission associated with the disk just in that low extinction window where that optical light is able to reach us. And as it slowly zooms in, I'll start pointing out some of the line ratio observations we got on this BPT diagram. And as we move further and further away from the center of our galaxy for like continuously along the bar, those line ratios get more and more enhanced until furthest away you get to these liner-like line ratios within the bar itself somewhere. And that's distinct from what that scutum cloud part that I was pointing out near the end is gas that's kind of associated with more local diffuse ionized gas, warm ionized medium that I was initially talking about, the more diffuse layer that's kind of like near us. So very distinct from that, the gas near the center of our galaxy in our bar is this liner-like gas that is not the same as the diffuse ionized gas, warm ionized medium kind of stuff that we see from leaky H2 region type of low density gas that kind of is everywhere. Since we have a model, we can like look at that model and make mock observations of it. So what this figure is showing is if you just have that some uniform density with a scale height and flaring associated with it, what would we be able to see in H alpha if you actually account for the dust distribution between us and galactic center? And this blue region is what we have seen with WAM, which is like basically the only thing that we would ever be able to detect because the extinction is too high to be able to see anything else. Maybe up here it's very faint. We haven't necessarily been able to see that, but that would also be farther away just from the projection of the bar towards us. So we really are like seeing this in the only possible place that we could see it, which I think is fun. But we have like some other measurements from the model, like the mass of ionized gas, which is substantial, like 10 to the 6 to 10 to the 7 solar masses of ionized gas in this bar region. And yeah, this is just kind of another schematic view of that tilted disk kind of structure, this geometric approximation for it. The flaring element is the ionized gas. The non-flaring part in the middle is neutral gas. We can think about like what can be ionizing all of this gas. In the solar neighborhood, we need about 10 times as much ionizing flux as we require in the solar neighborhood to ionize the diffuse ionized gas in our local environment, which seems pretty reasonable to do in a galactic center environment. Or another way to think about it is, there's the CMZ, the central molecular zone, that has lots of star formation and no stars. If we take about like 5 to 10% of that radiation and let it leak out of the CMZ in a radial kind of way, that would also account for the amount of Lyman continuum we need to ionize all of this gas. So it seems very feasible to ionize it. The exact kind of situation on how it's ionized is still kind of some work in progress, but it seems quite feasible. Right, this is where maybe I can take a little question break if anyone has some questions or thoughts.
Feel free to put your questions in the chat or raise your hand. Just to begin, I have a quick question, TK. Maybe you will be covering it later, but in your model, do we know how far it is from the galactic center, like in terms of KPC or physical unit?
I don't remember if I quite have a good picture for it. I'll just show this real quick. So the along its major axis is about 1.5 kiloparsecs in length, and for our distance to the galactic center is like 8-ish kiloparsecs. The closest reach of it is like 7 kiloparsecs or so. So it's not super far from us, but it's like right near the center of our galaxy, about that distance. Any other
I think
thoughts
Prof has a
around?
question.
Yeah, you mentioned that WAM has high spectral resolution. I was wondering how high.
Yeah, we see about, for like H alpha, it's around 12 kilometers per second in that space.
Awesome, thanks.
So that's really important for that telescope, especially because we can remove atmospheric um, emission explicitly by like as subtracting Gaussians within our spectrum as opposed to needing to do a very separate process.
Cool. Thanks.
I don't see any more questions, so maybe.
Great. I will continue. So now what I want to do is kind of connect this to other things at the center of our galaxy, like the Fermi bubbles. This may be a map of H1 gas that you have seen before. Jay Lockman and Naomi McClure-Griffiths put this together. Looking at H1 as you approach the galactic center, just looking at kind of tangent point velocity gas. So as you're going from the outer regions towards the center, you're filtering by different velocities, and that should get us closer and closer to looking at the center of our galaxy as you approach the center. Even in this plot, the big kind of message in that original that paper was the fact that this gas is kind of flat and then flares afterwards. And that kind of lines up with the Fermi bubbles, which I'll get to. But another kind of aspect hidden in this plot is this tilted, warped nature of the H1 distribution. It's not all kind of smooth and flat in that center, but it also kind of like juts in and out of the plane. If you do a different kind of fit or a different kind of filtering of the gas, instead of only looking at tangent point velocities, we can also look at these as velocities that are kind of associated with this bar, this tilted disk region. So if you filter by those velocities, you see a lot more of this tilted, warped gas that's associated with this tilted disk structure that I'm talking about. So this is a combined picture of both of those, that tangent point velocity gas, plus a little bit more of the gas in the very central, like 1.5 kiloparsecs of our galaxy that shows it's actually like a lot more puffy in that region, but it's very distorted and warped and tilted in this way. And this ties into a lot of work that Francie Cashman has done recently, also looking at this region in Galactic Center. And we can ask, how does this all relate to the Fermi bubbles that like also exist in this space, occupy this space? We think the Fermi bubbles might be kind of, providing a source of pressure to compress the gas in the center, though also the bar has, a higher concentration of stars, so there's more gravity and there's more, the gas should be thinner there as well. So there's a lot of things happening there. We can try to like piece together what is the complete picture of the gas in relation to the Fermi bubbles and the bar that is impacting everything we see. I always like going back to this view of the Fermi bubbles from the Fermi telescope. It really shows how hidden they kind of are in a lot of ways. It requires lots of filtering to remove our foreground between us and galactic center. But then you see these really nice biconical lobes. Now we also see them with Rosita. And it's become quite consistent with this biconical outflow of material from the center of our galaxy. A lot of that initial work to like confirm that it is in fact outflowing gas comes from UV absorption line measurements using HST. Andrew Fox in 2015 looked at one particular quasar sightline towards this PDS 456 background quasar, where you can see very clear signatures of both blue shifted and red shifted at high velocity gas that is very consistent with this biconical outflow that shows that there is gas kind of like flowing out from that center of the galaxy. What we did is also tried to look for this in H alpha emissions. So we know that there's ionized gas at these high velocities, these high, I'm focusing on the blue shifted velocities. We looked with WAM, with the Wisconsin H alpha mapper, in both H alpha and nitrogen 2 at doing some really deep exposures and stacking over much longer periods of time to get even fainter than what we normally have with our survey, and found H alpha and nitrogen 2 emission at these very high velocities that exactly match the velocities of the UV absorption features that we see. And that's really powerful because in the same sightline, we have both absorption measurements that are proportional to ionized gas density and emission measurements that are proportional to ionized gas density squared from recombination lines. And that gives you a model-dependent kind of constraint on many different physical conditions, like a characteristic density or path length of the gas that we can constrain directly. So we can, like looking from the data that Andy Fox had, there were many silicon lines that were fit, so we can combine them to estimate approximately a total ionized hydrogen column. Based on the H alpha, we have an emission measurement, and we can look at some 3D dust maps to do extinction corrections. And we also have like a rough metallicity estimate or constraint from looking at both the combination of nitrogen 2 and H alpha. We think we're seeing about 30% solar metallicity gas in this region. All of that with relatively minimal number of assumptions, we can get these kind of direct measures of ionized gas density, path length, temperature, and pressure. And we find densities that are quite high for being so high above the plane of the midplane of the galaxy. Temperatures that are fairly consistent with what we would expect, but pressures that are also quite high. So we see kind of like overpressured, overdense gas in this region. The other real benefit of doing this with emission is that unlike doing this with absorption line studies where you have to have background quasars and you have sparse pointings and directions, or with H1 looking at neutral gas where the gas has been shown to be quite sparse in that region, apart from some smaller kind of chunks of outflowing clouds. H alpha in this way, we require no background source. And we're starting to see hints that the ionized gas that H alpha is tracing at these high velocities is kind of everywhere, at least a little bit more. So we can start to maybe put together a picture of the spatial and kinematic extent of the Fermi bubbles in an extra dimension and make a continuous mapping of that Fermi bubble gas in velocity space and spatial space using emission lines instead of just absorption lines. We tried doing this also with the GBT. We looked at radio recombination lines in that same direction towards PDS 456, hoping to see a different tracer of that emission. We had like 30 hours of deep time just at that single kind of staring at that one spot. We weren't able to see anything. We had a non-detection, but it was still a very powerful non-detection that let us further constrain those densities and things I was saying, especially because the lower resolution is better matched, or the higher resolution with GBT compared to WAM was better matched with the scalings of what we're looking at with absorption lines. But it looks like optical emission is a really good bet for how to try and map and understand the spatial extent and kinematic extent of the Fermi bubbles, which is exciting. In the future, what we're kind of hoping to do is, look at all of this a little bit more carefully. We have these like very large pressures that are associated with the gas that we see. That's pretty consistent with model predictions of either a hot halo or Fermi bubble shells that Miller and Bregman have suggested in the past. But it like suggests that we're seeing maybe an overpressured zone, an overdense zone of gas. And it's unclear kind of how that's all distributed in within the Fermi bubbles, around the Fermi bubbles, whether it's kind of volume filling or in a shell, yet to be determined. The other thing I want to kind of point out is like all of this still connects back to that liner-like line ratios. The fact that we have these weird line ratios of optical emission in that bar region means that there's something different about the radiation field, about the source of ionization happening there. And that both lets us kind of better constrain what liners are from an extragalactic perspective and gives us an opportunity to really understand what is the radiation field in the center of our galaxy. And we can do that with both UV absorption, like towards the Fermi bubbles that I was talking about, and optical emission with WAM. We're working on this in an HST archival program. Myself and Francie Cashman and Andy Fox are trying to put this together a little bit more carefully. And I also just want to like spend a little bit of time doing a little shout out to a close collaborator of mine, Lewis McCallum, who has been doing photoionization in 3D, not just looking at one-dimensional photoionization. The photoionization kind of I've been talking about in terms of modeling it has been from cloudy in 1D. Lewis has been developing 3D code that works wonderfully and has some really cool results that I want to share on that side. So not in the center of our galaxy, but on our local neighborhood, we have really detailed, really high resolution 3D maps of dust. These are ones from Edenhofer in a 2024 paper that I'm showing towards the right. This is a face-on view where at 0, 0, the center is our location, and it goes out about 1.5 kiloparsec in radius from the sun, where we have these like high precision maps of where is the dust in 3-dimensional physical space. So we know where the dust is. We also know where most of the massive O stars are that do most of the ionization for the diffuse gas in our galaxy. So what Lewis did was kind of just took that and asked, what if I can make the simplest assumptions possible? What if we just track ionizing photons in 3D, placing them in this dust map world based on where those O stars are, and just see what the O stars can do. How much ionization does that do? How does that compare to what we see? And it turns out extremely beautifully that just with knowing where the dust is and where the O stars are and only doing ionization from O stars, you can almost entirely recreate the H alpha sky that we see with WAM. So on the left side is what we see with WAM, with like some circles and shapes around some known features, H2 regions, structures in our galaxy that we know within like about 1.5 kiloparsec from us. And the right side is the simulated H alpha sky from Lewis's simulations that look remarkably consistent, very qualitatively similar. There are a few parts that are brighter. There are a few parts that are fainter. But this is only looking at 1.5 kiloparsec away from us and only doing ionization from O stars and making it many super simplifying assumptions. And yet it still creates a really remarkably true to reality picture of what we see with H alpha. Lewis is great. He's on the job market. He's just finishing his PhD now. I think he might be Dr. Lewis. I don't remember when he defends, but wonderful person on the postdoc job market. Yeah. I also just want to show, because you can do this in 3D, Lewis has made these great videos of going through and looking at optical emission, H alpha, sulfur 2, oxygen 3, in 3D, where you kind of can glide through space and see all of these individual pockets of H2 regions, some regions where that ionizing radiation has escaped further to create more diffuse emission. I'll go through it one more time. So this is starting in our location at the sun's location and kind of turning every now and then and going through different known H2 regions, known cloud complexes and things. I think it's just quite mind-blowing how, where we've come from where we've started. We have this like pictures of 3D gas and dust starting to come together. This is just another 3D rendition from that same simulation, just looking at the Orion Eridanus superbubble in just H alpha emission. But again, lots of like 3D features. The brightest regions are kind of concentrated around known O stars, and then there's more diffuse gas that shows up around there. But we see supernova remnants, we see H2 regions. It all just kind of shows up really nice with very few assumptions and things going on, which I think is just remarkable. So look out for this paper. It should be out soon. It's in review currently. I'll just go back to this page. I think I'll end here. It's just kind of like wonderful seeing how with just O stars and knowing the dust density, we can make accurate WAM H alpha sky maps. And you should consider hiring Lewis if you're looking for a postdoc. Thanks.
Thanks, DK. That was very interesting. Let's, yeah, it's time for questions. Since people are thinking about questions, maybe I can start again. So I just wanted to get your thoughts on this beautiful 3D map. But most of the time when we are comparing things, we are just squishing everything in at least in one dimension. So I was wondering, have you guys thought about if our line ratios get impacted by all these different things being added up and then, you know, make the ratio to add everything up versus when actually they are like being produced at different levels at different places?
Yeah, that's a really great question, and definitely something I've been thinking a lot about. Uh, I don't think we've necessarily gone through in the simulations. Lewis has been adding in the other tracers beyond H alpha more recently, and we haven't spent too much time looking at how that changes depending on, for example, like how much in distance you integrate to all those kind of projection effects that would take place from that. I think that's a really great thing that is very testable in a situation in his simulations. And I would like to do. But it's definitely something I think about a lot is how much of just the angle we're looking at things, the like projection that we're looking at things influence what we end up seeing. It was really tricky with Galactic Center, the bar kind of tilted disk stuff in the same way because yeah, everything was oriented weird, tilted, warped. Um,
Oh, thanks. I see a hand, but I don't see.
I think
Oh,
it's Christy.
Christy.
Hi, DK. It's great to see you again. Very,
Hi.
very cool stuff. I was curious about maybe two things. One is, you mentioned that the abundance of the gas in the inner part of the Milky Way had like a 30% solar abundance ratio. And that seems kind of surprisingly low. Do we have a clue to how that might have come about? Like, is it related to this tilted disk? Is it like an infall event or?
The 30% number is for that like one Fermi bubble kind of direction. That's about like 10 degrees above like the direction of Galactic Center and like it's quite far away from Galactic Center in height. So it's not, I wouldn't necessarily say it's like 30% metallicity gas in the Galactic Center environment necessarily, but just this like one region. I also would say like it's a really weak constraint of metallicity that is I wouldn't put my name to that metallicity if someone wanted to use it really. It's just like the best guess we can do based off of having some emission lines and a few other things. And there was technically some MCMC modeling that went into it, but like it's not a very powerful constraint.
Now, I was wondering what sort of physical mechanism would do that, because in that Fermi bubble region, why people think that's outgoing stuff. You'd think would be very high in metallicity.
Yeah, I think part of it plays into like what is doing the outflow, like whether it's starbursty or unclear. But yeah, I agree. I would recommend not to read too much into that metallicity for now. I think we need more information to really actually get a metallicity measurement. That's not yet really possible with the absorption lines. There's not enough things to do it accurately with the absorption lines so far.
Yeah. And there was a statement somewhere, which I was just looking for and couldn't find, that of the large mass of gas, hot gas in the Fermi bubbles. Does that sound familiar?
I am not honestly sure about like the mass of hot gas associated with the Fermi bubbles. Maybe that kind of information could be in either of these Miller and Bregman papers and their models. I don't know of a good estimate of that or have any kind of intuition for what to expect for that, to be honest, though.
I guess it'd be really small because just hot gas in general doesn't have a very big fraction of the mass.
Yeah. Yeah, I would believe that.
Any other questions? If not, let's thank DK once again for the very interesting talk. You can find this talk on our YouTube channel. Our fearless leader, Xiaowen, will tell. Maybe they already know where to find it, but
It will be on the COPAC website, the DGCE website. So that's the most secure place. Well, thank you again for a wonderful talk. And just remember that the next talk will be on March 27th at the same time by Dr. Daisuke Nagai at Yale University.
Right. Thank you, everyone, and have a good evening.
Thank you.
Thanks.
Thank you.